Yes, your screen is visible.
Yeah, I think I need
Hello?
to.
Yeah, yeah.
Yeah, I
So
think I
let me
need
just
to
briefly introduce.
change
So you can.
the mode, I guess, right?
Hello?
Uh, so are you able to see the full screen view?
Yes, yes. Can you
Okay,
try
okay.
to do the slide transition so that we can see the moment of couple of slides? Then yeah, yes, yes. Okay, so before you begin, so let me just briefly introduce the speaker. So today we have Professor Preeti Malakar. She's an assistant professor in the Department of Computer Science and Engineering at IIT Kanpur. So prior to this year's postdoc at ANL, this is Urban National Laboratory in USA, and she was also visiting affiliated Lawrence Berkeley National Laboratory, and she did her PhD from ISC Bangalore, and she works in the areas of high performance computing and related areas. So over to you, Professor Preeti Malakar. For the session.
Yeah,
So
thank you,
she will
Vishwesh.
conduct the three four. You have three sessions, right?
Yes.
For this week. Okay. Thank you for agreeing to our lecture and conducting last session.
Oh, thanks, Vishwesh. So, hello, good morning, everyone. So this first lecture I have planned for a little bit deep dive into the architecture of distributed memory systems, and I'll say what I mean by that. And the next lecture is more towards programming. Okay. So this is something that you have already heard about. That is, we mainly, when we talk about parallel computing, which is ubiquitous now, right? We mainly talk about two different platforms or architectures. One is shared address space. That is, you're talking about one node here. And this node is, of course, today we have multi-cores, and you can run your program, which can be multi-threaded or multi-process paradigms, which we'll talk a little bit later. And so we use the entire node as if it there's to the OS, it's just one memory address space. So every process or thread can access any memory in the node. However, one thing to note in today's architecture is that the time to access certain memory words may be longer, and I'll talk a little bit about that. So the other kind of platform or parallel computing platform is message passing, using message passing, because here we have kind of different nodes. So these are different computer nodes. You can even think of it as two different or three different laptops. You just need a wire to connect the laptops, and you will kind of build your own mini cluster. So here you have multiple processing nodes, and of course there is no shared address space, right? Because the memory is local to this node. This node has its own memory, and so on. So you need some kind of send receive operations, some kind of exchange, message exchange, through which you can exchange data. And we'll talk about both these paradigms a little bit in the next lecture. Okay. So okay, so this is something that you already know about. Gordon Moore was the co-founder of Intel. He had predicted the number of transistors in a chip will kind of double every 18 years, and that kept on being true for quite a long time. And today people are talking about post-Moore era. Why? What happened around 2002 was vendors started thinking about packing more cores into a chip, because we hit different kinds of wars that we've already heard about. And so we have multi-core systems these days, and one node has up to like more than 50 cores today, and we'll see how complex can just one node be, and then we are talking about multiple nodes, so how complex can that system be? So we'll look into that. Now, a few things to keep in mind is, so here you can see that the clock speed kind of saturated long time back, and so what we have been, but still the total throughput that you're getting is sort of increasing because we have been packing more cores per socket, and you can also see number of cores per socket have been increasing, right? So there are more and more cores in just one node, so that makes the node pretty complex, and we'll look at some pictures. So as you know, all you have is these kind of main components. You have the processing unit, which does your computation, right? And then you have the memory. You need the data, the program to store and access the data, right? Program and data. And then you have the network. Because like I said, we have multiple cores, and so you need some networking to access for data movement between processor, memory, and so on. And then you have the storage. So storage is also complex when you think about multiple nodes. So we'll talk a little bit about that. So here is a somewhat old diagram which kind of shows that very early on there was this, there's a whole concept of symmetric multiprocessing, right? Where you have same to the processor, the memory is kind of the access time to memory is similar, but that's no longer the case today. We have what we call as non-uniform memory access, NUMA architectures today, and we'll look at some example systems. So some people believe that almost 30 years ago, truly SMP computers were built, and this is just one picture of this gigantic machine. So you may know that earlier machines used to be really huge. Just one system used to be pretty big. So now, when we talk of memory, right, which is where all our data is, right? So you may have seen this kind of diagram, and what you are already aware of is that it takes, of course, less time to access cache and 100x more to access the main memory. But the picture is even complex today, right? Why? Because we have, so this is a die shot of a real system, AMD Bulldozer, is from almost 10 years ago. We have memory all over the system. We have different chips. So here in the picture, you can see there are four Bulldozer modules, they have called, packed onto this chip. And there are multiple L2, L1, L3 cache scattered all over the system. To understand it logically and a cleaner diagram, you can take a look at this picture. So this is the output of a tool called LS Topo. And what it gives us, what it shows us, it shows the memory topology of the system. So here you can see this is just one node. Remember, we are still talking of just one compute node. So it has two sockets, and that hosts, each of them hosts two NUMA nodes. So you can see it's so this is what is mentioned as NUMA nodes. So there are two NUMA nodes per socket, which means that this particular unit is somewhat compact. So it has the memory, caches, and there are 8 cores here. So every NUMA node has 8 cores. So when any thread or process access memory which is present in this NUMA node, of course the access time is much faster than if it were to access the cache or memory, whatever data is present in some other cache or memory, right? Okay. So, so this is another system where you have two NUMA nodes, 6 core in each of them, and of course you need a interconnect, right? And they have, so here is another diagram where they have packed 2 of these, and so you need like a NOC, a network on chip, which helps in the data movement among the cores, right? If you want to send data among cores, or you want to talk among so send data from one memory with the memory which is remote to to a core, you will need this networking which is present on the chip. Fast forward 5 years later, this is a system built by Intel. This had it has about 72 cores. There are various versions. Some of them have 64, 68, and 72 cores. It can up to 72 cores it can have. So let's spend a few minutes on this system. It's a bit complex system. So what you see here, so this part is just one tile. This is the zoomed version of this. So this you can think of as one tile, and there are 36 tiles. Okay, so 36 tiles connected by 2D mesh interconnect. Now, if you have 36 of these units, you need some kind of connections, uh, uh, a good scalable interconnect, and they decided to go with 2D mesh. So 2D mesh is nothing but just like a matrix, right? So this each tile basically has two processing cores, and that's why I said it can host up to 72 cores. These two cores, they share the L2 and they have private L1 caches. Anyways, so the details are, of course, you can look up the paper by Intel on this. But the primary point here is, so you have these multiple cores spread across the chip and the node, and there's also distributed, memory. Although it's still a shared address space platform, it's a single memory to the operating system. It's just a contiguous view of the memory, even to the application. But the physically, it's spread across the system, and that is why sometimes applications which are NUMA aware, right, they perform better. So there's a field of research which talks about NUMA aware placement of processors and threads on this compute node, because you can see this particular node itself, just one node is a very complex entity, and they, after designing all this complex complexity into one node, they were able to achieve 1 terabyte, 1 teraflops from just this one compute node. And so there are some systems installed in some supercomputing sites which use this node, so this architecture, Intel's KNL. Okay, so coming back to this figure, which means when we talk about memory access time, we have to be a little careful now. So if you are accessing the memory which is local to the NUMA node, probably you will get 150 cycles, which is what was there in this diagram initially. When we are talking of memory which is in the other NUMA node, it's probably going to take a little longer, maybe 1.5x, right? And why are we talking so much about memory is because the processing rate have tremendously increased. As you know, it has exponentially increased over the years, whereas every other component has been lagging behind. The DRAM access time, the networking speed, and so on. So our data, where's our data? It's in the memory, it's in the storage, primary, secondary storage, right? So we have to be a little bit more careful when we write our codes, our applications. Because just because the compute speed is, I'm getting a lot of compute speed, it doesn't mean that your application will automatically run faster, right? Okay. So just to summarize, this was our, this is a simplistic view of, the NUMA node. And when you have to talk among, two different NUMA nodes, you need some kind of network which transfers your data. Okay, so that was one compute node, right? Now, distributed memory architecture, if you in general, it means you are talking about multiple compute nodes, probably several hundred thousands of nodes. So how do we build such a system, right? We saw one node itself is very complex, right? Now we'll talk about that for the remaining slides. This was one node, one example, right? Compute node, and you have two sockets, and we have seen, okay, we have multiple cores per socket and per Newman node and so on. Now here is, in the bottom of this figure, you can see there's a box which says Gemini router. This is what is going to connect this node to the other nodes, and you may get something like this. So this is just a simplistic view of, you can use some routers to connect to other nodes, and then you can build a cluster of compute nodes, right? Okay, so okay, maybe I can pause for a minute here. So any questions so far? I'm sorry, I'm not seeing the chat. So if you have questions, maybe you can unmute, or we can take at the end. Okay. So, right. So let's talk a little bit about this routing, which plays a pretty important role in these, connecting all the nodes. The simple way to connect all the nodes would be we connect everyone to every other node, right? So every node can talk to everyone else, but that's very costly, right? If you think about, I mean, even a few hundreds of nodes, it'll involve huge amount of network links, and that's why its cost is going to be tremendous. So that's why there are these specific interconnects that vendors have developed, and I'll just show a glimpse of that. So here in this figure, I have, so this is figure from Cray, which shows two different interconnects. One is C star, and the top figure shows C star router. Basically, this is an ASIC, this what you see as this orange color or brown color box here with 6 different links, right? So the difference between these two routers, one is the C star router and the other is the Gemini router. So Gemini is the next version of C star. So C star used to connect just one node, and Gemini connects two nodes per ASIC. So anyway, so one question here is, you see here there are these X, Y, Z, and there is this dimension, right? So can someone maybe, if you can unmute and answer, like what do these, why are these required? Any idea? So what do these basically imply? So I'm not looking at the chat.
Maybe
Huh, yeah.
maybe X and Y for within the node and Z for outside the nodes.
No, so basically, so this we will think of this as kind of one entity. Sorry, so we can think of this as one entity, and XYZ are all other routers. Okay, so here in this figure we have, like, if you see, this is the Y dimension. They have mentioned this as the Y dimension. So this figure has, in Y dimension, we have placed two nodes, and you have the Z dimension going up and X dimension coming out of the plane. So you can place your routers. Each of them will again connect to two nodes, right? And that will internally basically build the connections between all these nodes. And ultimately, what you get from this is actually like a 3D, you can get a 3D mesh, you can get a 3D torus, and so on. So this was actually used in some of the supercomputers. But one thing to remember is, so we have these compute nodes that are probably manufactured by some vendor, and there's the networking, this is probably manufactured by some other vendors. And so compute nodes come in like a package. It's like you have racks, or you maybe have boards or something. So all the nodes are kind of plugged into those boards, and then boards are probably stacked up, and you have racks of compute nodes. There can be different terminologies used. So here, what they have used is compute blade. So this diagram, what basically they are showing here is, so you have this compute nodes here, and then you have this network blade here, which basically are these routers. Okay. So we saw every router is connected to two nodes. So you can see these arrows, the black arrows. You will see every router they have connected to 2 nodes, right? And depending on where is that location of the node, so basically every node will have a coordinate, right? 0 0, let's say from 0 0 0 to n cross n cross n, if you have a n cube kind of 3D mesh or grid or torus. So every one will have every node, right? Every compute node has a coordinate, and depending on its location, you will be connecting it to a particular router or to some to a router in which, and internally that router will be connected to those other routers which are connected to its neighbors basically. Okay. So you can see there's some amount of complexity here, but anyways, the point here is you build these nodes, you stack up these nodes, and then you have to wire them up in a certain way, which basically determines the topology of the system. And what they actually look like is very scary, right? Messy system like this. So this is a real picture of a real system from NERSC. Okay, so you can see here. So let me probably show you what I meant by rack here. So this front. So this is the back side of this system, and the front what you will have are these the compute boards, the computing nodes in some sense, and yeah. So this is this just to show you like how complex these systems can be. But on the outside, what you see in many papers and everywhere is this pretty, casing, which shows blue waters, Edison. So these are name of these big systems, also called as supercomputers, right? Internally, they'll have some kind of topology. So remember, there is no system which has like all-to-all connections. There's always a kind of a regular topology. So the left side system, it has a 3D torus, which we just kind of saw. And the right side system, it uses a topology called dragonfly. So what it does is it connects subgroups of nodes to subgroups. So it kind of virtually it thinks of the nodes as rows and columns, although there is no really, the nodes are not exactly placed as rows and columns. But physically what it does is every node of the row is all to all connected, but that's just one row, and then every column is all to all connected, and so on. But anyway, so this is like a hierarchical network. It's a lecture in itself, so maybe you can look up if you are interested. Okay, so what we saw till now, we saw a single node, pretty complex, right? Example is this Blue Gene Q chip, and we saw that we have a lot of networking, and that leads to build up this huge, massive systems, which are like, $1 million systems, takes up space which can be as big as a tennis court, and takes at least 5 to 6 years to manufacture, install. Physical installation, and then the software installation, system software, and then it's ready to use for users. Okay. All right. So now that we have kind of looked a little bit into supercomputers, one interesting thing that you should know is there's a list of the most powerful systems in the world, which is maintained in a website called top500.org, and it's updated every 6 months. So July one list is updated, and November another, it's updated again. So this is the latest list, and so there are just 500 of these listed, but of course we have all over the world there are many hundreds of thousands of supercomputing sites. So here you can see this. The first system is, I think, from Japan. Yeah, supercomputer Fugaku. So I think they were there in the top one, the last ranking also. But anyway, so what they show is they basically rank according to. So I'll come back to the question on programming language. So what they do is they rank according to the maximum computing speed that you have, or the floating point operations, right? The number of floating point operations that you can do per second. That's what is shown here in the fourth and fifth column. And you can see we have reached close to like a 400 petaflops. Okay. And another interesting thing that you can see is the number of cores, mind-boggling number of cores, right? Interestingly, it doesn't mean that if you just pack a lot of cores, it gives you the highest performance. An example you can see here, the system from China, Sunway Taihu Lite, which was actually #1 for quite a long time. So it has 10 million cores, but you can see all of the systems, the 1, 2, and 3, they have less number of cores, and there are various reasons for that, which I cannot go into detail now. But anyway, so this is a list which maintains systems from all over the world, and even we have 3 entries here. Well, 3 is a really small number, but anyways, we have 3 entries here. This latest edition. One is the first one is Param Siddhi, which is in CDAC. The second one is Pratyush, which is in Meteorological Institute in Pune, IITM. And then we have another weather forecasting, which is in, I think, Noida. So this is Mir. So anyways, so this is just for your information. Another interesting fact about these systems are very recently, I think last year, the lowest entry. Here you can see the curve here. The blue curve shows the lowest, the 500, the speed of the 500th supercomputer, and the green dot shows the speed of the top, the most powerful, the first position supercomputer. And you can see the lowest speed is 1 petaflop already. So if you have to gain an entry, you have to build at least a 1 petaflop machine. Okay. All right. So before I go forward, I'll just answer the question because I saw in the snippet. So the question was, I think, what programming language is used on these systems? The 2 main programming languages that are used, if you talk of language, are C, C++, and Fortran. Okay. And when I talk about programming language or models in the next lecture, I'll tell you a little bit more on that. Okay, so I thought we can spend a little bit time in looking into a supercomputer that was built 10 years ago. So this was built by IBM. This was called Blue Gene Q, and before that they had 2 other systems. The first one was called Blue Gene L, which was built around 2004-ish, I think. Then the next one was called Blue Gene P, and then the successor and the final one actually in this series is Blue Gene Q. So initially they had a small, so what they do is they do a smaller installation and they, try to see if everything is working fine. And then oftentimes they expand the system. So here you can see November 2011, they had a 4,000 node system installation, which was number 17 at that point. And it had only 600 teraflop compared to, today's number 1, right? So it was number 1 on Graph 500, which means that there is it was really good at. So it gave the highest speed for benchmarks, which are used to calculate this different list, which is called Graph 500. So they are more towards applications which are like graph applications. And it also was number 1 on the Green 500, which means it consumed very little power. Okay. So they expanded it 6 months down, and they were number 1 with 96,000 nodes in one site, and there was another site where they had 48,000 nodes, and they were number 1 and number 3. So actually, the system was really good, and that's why I thought I'll spend a few minutes here. And you can see it's such a nice scalable system. You have exactly half the number of nodes, and you have exactly half the compute speed, the peak speed here. So the number 1 had 20 petaflop, cut down by half, you have actually 10 petaflop system, and even the power scaled down pretty nicely, right? So let's look at just a little bit into the hardware. What goes inside ultimately is your processing, right? Processor. And so this has, of course, billions of transistors are required. It has something, so IBM has something called power architecture, and so it has this is built on the power architecture. Uh, there were 18 cores on chip, but they used to keep only 16 cores active, and on one core they would run the OS, so that the OS functions do not interfere with the application, the applications. Because so one thing to remember is supercomputers are typically used for running very high compute intensive scientific applications. So sometimes the OS, OS runs many background jobs and threads, so that there is no interference from the OS processes. So they run OS on just one core, and then one of the cores is just redundant as a backup. And so from one core they got about 12 gigaflops, and this whole node they got about 200 gigaflops. So this is just one compute node. Okay. So inside this node, of course, like I mentioned previously, you have a networking. So here, what you see in the middle of kind of this figure is the crossbar. Which is another kind of interconnect. They use this to connect between all the processing units and so on. And what you see below here is actually a messaging unit that handles all the traffic that goes outside the chip. So what we saw, like we have to connect this node to several other nodes. So many details of this are proprietary, but however, there are a few things that are published. So one of the things is it has a 5D torus, which means it is connected to 9 other nodes. Okay, so there are basically 10 communication links coming out. So one of the link is actually used for I/O. So there's 11th link as well. Each of these were about 2 Gbps unidirectional, and both ways you can get 4 Gbps bidirectional bandwidth, network bandwidth. And the peak total bandwidth was about 44. That is, you can push data out of the system as well as receive data at 44 Gbps, because you have 10 links. So that kind of scales up amount of data that you can push, because remember, our computing speed is very fast as compared to the network. Okay, so that was one node. What this figure shows is 32 such nodes packed into what they called a compute node board. Now, here, if you see these, so I think you can see this arrow. So these are the nodes which we just saw, and then we have a lot of other components, right? We have the networking, the fiber optics cable here. So that is required for all the networking with the other nodes. And we have to cool the system. So there are these water pipes, which you can see this thick black line. So anyway, so just one node is so complex, and then you have 32 nodes packed into this, which they call like a compute board. So that is also very complex. And now we are talking of what? We have to reach 96,000 nodes, right? So how do we do that? This is like a simple diagram that they show. What they do is, so we saw one node of BlueGeneQ. Then we saw 32 nodes were packed into one node board. And 16 of those node boards are packed into what they call as a mid-plane. So 5 and 2 nodes are in one mid-plane, and 2 such mid-plane is what they call as a rack. Okay. So virtually you can think of this as like you have 5 and 2 nodes here, 5 and 2 nodes here, and this is one rack, and one rack has 1K nodes, and you need 96 such racks to build that top supercomputer, Sequoia, which they called. What goes inside are these, of course, the chips and the networking. So these are the primary components that is used to build such a massive system. Okay. So going forward, so now comes the main point about networking, right? We have built a system which, I mean, okay, we have this 5D torus, fine, but how do we, 96K, so how do we arrange that into a 5D torus, right? So we have to think about that, and that's what you get finally as the decomposition of the 5D torus. So here what you show is just what you are seeing here is just a midplane. Okay, so midplane is, remember, 5 and 2 nodes. So we have 4 nodes in the A dimension. So these dimensions were called A, B, C in this system. So 4 nodes each in the A, B, C, D dimensions, and then we have the last dimension, which was the E dimension, which is on the same node board where you have all these 32 nodes. That was just 2. Uh, a quick thing about this, the networking that we are talking about, because the networking speed in some sense determines the overall, how much overall throughput that you're getting from the system, how fast your application can run on these 96 nodes, because the application has to, your program, it's probably scaling up to all the 96,000 nodes, or it may be scaling up to 1,000 nodes. And these 1,000 nodes, these are not independently running. In some sense, they are running at sync. They are coherently running one application, right? So this networking speed is pretty important. So in the previous BlueGene L and P, we were in megabytes per second, and finally in BlueGene Q, they had this link with 2 Gbps per second, which of course gave massive scalability to this system. Now, the other thing was the previous systems, they had 3D torus. So with this system, they decided to go with the 5D torus. Why? Because here are a few things that you should know about the interconnect, which are these terms in the first bullet point I have here. So basically 5D torus has a lower diameter, higher bisection width, and lower latency. So let's think about this a little bit. What do you mean by diameter of a network? And so can someone maybe unmute and answer? So what is, if I draw a system like this where, let me use a different color. So you have these 4 nodes. What is the diameter of this system? Although this is not like a regular topology or anything, but can someone tell what's the diameter of the system?
Yes, ma'am. It will be 2 in this case.
2, correct. Who is saying that they cannot see the pointer? Is everybody able to see the colors, the figure that I'm drawing here?
Oh, yes, ma'am.
Yeah, okay. All right. Yeah, okay. So, so it's 2, right? So imagine if it's a 3D torus, so the diameter would be, you go 1/2 on one dimension, or maybe I should use maybe I can expand this a little bit. So okay, so let's just consider this 2D mesh, right? Okay, so 2D is easier to draw. So you will basically be going 1/2 if you have like, for simplicity, let's say 2n cross 2n, 2D mesh. So you will go n in one dimension and then n again in another dimension. That would be your maximum, that would be the maximum distance for a for a 2D torus, not mesh, sorry, torus. So torus is basically you are connecting the top and the bottom element of this grid as well, right? So which means you just have to traverse half in one dimension and half in another dimension. Okay. So which means if you think about it, if you have to build the same number of a system where you have the same number of nodes, and in one system you use a 3D torus, and in the other dimension, in the other system you use a 5D torus, so your diameter in the 5D torus will actually be less. And so you can think about it if from the analogy of 2D versus 3D, and probably you can draw later and think about this. But anyway, so the point here was that they decided to go with 5D torus because it gave a lower diameter. It also gave higher bisection width. Now, what does bisection width imply is, so let's say you are running, so this is a massive supercomputer, right? 96,000 nodes, and every node has 16 cores, right? So often we do not have applications that scale to 96,000 nodes. So what typically is done is there are hundreds of applications running on just one system. Okay, so which means all the other applications, maybe let's say they are using some part of the system, and you need to, so you are also using some part of the system, and you I mean you may not always get a contiguous portion of the system. So some portion of the system, let's say if you think about direction north, west, south, so some portion in the east, some portion in the west, and so on, right? Now you need to, of course, you need to communicate among your east and west components, the 2, 3, or 4 components which are staggered all over the supercomputer. You need to communicate among them. So higher the bisection width of a supercomputer, there's more chance that you will encounter lesser delay, because you have more paths. In some sense, you have more paths from one section of the system to another section of the system. So this is a very kind of a simple way of stating the essence of why bisection width higher is important. Okay. And the last point here that is mentioned is high nearest neighbor bandwidth. Why this is important when they tried. So remember I told you that they take 5-6 years to build a system. Some of that time is actually spent in analyzing what kind of applications am I running on this system. Because if I'm not running certain kind of application, there's no point in building a system which performs good for that kind of application. So this is often the case. And so often it has been found that almost like several applications, they use this communication pattern which is called nearest neighbor. That is, you are communicating with your neighbors more than you're communicating with someone who is far off. So this is just a communication pattern. Of course, it's not the only communication pattern in the application, but it so happens that this often occurs predominantly in many applications. So that is why they have this selling point that we have built a system which has high nearest neighbor bandwidth, right? So that's very important. And remember, this is important because we are not connecting every node to every node. We are still using this 3D torus, 5D torus, Dragonfly, or some kind of interconnect to build this system, right? And despite that, we have been able to achieve maybe high all the good qualities of an application or a system. Okay. So with that, yeah, I'll move on to the next slide. Okay, so I already told you about the A, B, C, D, E dimensions, and I have just one detail point that there are some link chips on those compute node boards that I saw. That is a collection of 32 nodes, which are actually internally used to connect. Okay, so this point is pretty interesting. So on the chip, per hop latency, right? You have 16 cores. Per hop latency is on the order of nanoseconds. For this Sequoia system, which was the number one system I show, the 96K system, this is the A, B, C, D, E dimensions or the torus configuration, 5D torus configuration for that system. And for that, the P2P latency, the average is about in microseconds, right? For one hop, it takes zero 0.6, and for 13 hops, it takes 1.17. So what is a hop? It's just if you're communicating to just your physical neighbor, that is your whatever router you're using, like we saw in the Gemini router, right? Physically, you are connected to that next node that you will call as that is your one hop neighbor. Okay. All right. And just a little bit more in detail is, so one thing that we saw is there are multiple cores, right, on a chip. So all these multiple cores, they are running, of course maybe they are running the processes of the same application, but it doesn't mean that they are always at sync and they decide who will send the packet. It can so happen that every 16 processes that are running on these 16 cores, they are sending simultaneously, they are sending packets out of the chip or the node. And so they had this nice system of queuing. So they built a FIFO or a queue for receiving and for sending out, basically. So and they had this for per torus link. So A, B, C, D, E, 5. So they had a beautiful system where they placed it on the correct queue, and they sent it out of the correct queue and so on. So this helped a lot with the congestion problem and so on, and that made the system very nicely scalable. And I have just one final slide on this, which basically is about, the point is about, you have this A, B, C, D, E dimension. So before I go to such a big dimension, let me just ask you one simple question, which is, let's say I have these 4 nodes. I'm sorry about my not so beautiful diagrams. So I have these 4 nodes, and this is like a 2D mesh, right? And I want to send data from this node to this node, right? So let me just number. So 1, 2, 3, and 4. So I want to send data from 1 to 3. How many different ways are there? And what are the ways?
2 ways through
2
1,
ways,
2, 3.
right? 1, 2, 3, and 1, 4, 3. So this is just in 2D. So imagine in 5D, you have multiple ways to reach from one node. So that is why they have, so you need to have a routing policy. So remember in the few slides earlier, I showed this system, the KNL system, where I had shown you that there were 36 tiles which were connected by a 2D interconnect. This is just one node we are talking about. And they had, so what they do is they do a YX routing on the chip. So they go the Y dimension first, and then they go the X dimension first. So if you do a YX routing and you say that, okay, I will only do YX routing, then I will go from 1 to 4 and 4 to 3. Okay. And of course, a static routing policy may not always be good. So these supercomputers, they have adaptive routing and so on. But here, what I was trying to show in this figure is, so they have basically compared different, routing for these kinds of systems. So these are 2 different systems, and they have compared different routing policies. And you see that some of them, they give good performance, like 85% of peak, 91% of peak, and so on. So here, the point of the takeaway from this slide is that so much of hardware complexity we have already heard. On top of that, routing also, determines how good your application is going to perform. Okay. All right. We are talking so much about, supercomputers, 96,000 nodes. What do we actually do in these big, powerful systems? So there are some applications, quite a few applications, which are routinely run on these applications. These are science applications. One of them, one domain is a cosmology simulation. So this is This is an application called Hack, which was run on the entire Sequoia system, and it achieved about 14 petaflops. And this is another application which was heart simulation code, which achieved again 12 petaflops. So there are applications which scale up to the entire system, and that's their goal. They, of course, if you can use the system very efficiently, you are going to get your work done more quickly. And like I said, these codes are very compute intensive codes. They run for days, they run for hours and days. Okay, so we have recently so because this is an NSM sponsored workshop, so it's worth mentioning that NSM has been installing quite a few supercomputers in India, and there's just two of them. There are, I think, 5 of them in different IITs and other places. So Param Sanganak is an IIT Kanpur, Param Shakti is an IIT Kharagpur. So every system is slightly different. Param Sanganak has slightly fewer number of nodes than Param Shakti. However, both have similar peak performance. The Shakti was installed before Sanganak is installed recently. And this is something that I got from their website, nsmindia.in, which shows you the usage of the system. So you may have read about, CPU throughput, how much CPU utilization and so on, right? So that's one CPU. Here, what we are showing, what they are showing is how many jobs were running actually. I couldn't find a picture which shows how many nodes were in use, but they have a usage report which shows how many jobs were running. I think this is from 2nd November to 28th November. So it is very recent. So this is just a month, last month. And of course, you can see there's variation. Some days there are more jobs, less jobs, and so on. And you can also see that in the top system, the number of jobs are probably 3 to 4 times larger, higher, right? So this alone doesn't give a complete picture. Of course, the number of jobs can be high if even if you are giving jobs on smaller number of nodes. So then automatically your number of jobs may be higher. But on the other hand, they have slightly higher number of nodes. Okay, so with that, let's move forward. Okay, so let's finally, look at a detailed like a overview of this supercomputing system. So we talked a lot about the racks and all, right? That we have multiple racks. We can have 100 racks with each of them having 1,000 nodes and so on. But that's not it. So we know the processor, memory, so that is on the node. But some of the networking is on the node. And we also worried about the networking among the nodes. Now, what is remaining is our storage, right? So here on the right side, you will see there is something called primary storage and so on. So you can ignore archival storage. Archival storage is just for long time storage, but mostly the applications, they work with the primary storage. So what that means, so we are, if you're have been working on single node systems, so we think that, okay, our hard disk is attached to our system, right? None of the supercomputers have any secondary, any HDD attached, any hard disk drive. None of them is attached to the compute nodes. So it's always a storage system, a network attached storage system on which most likely there's a parallel file system mounted, and you are going to access that from your compute nodes. Now look at this system. So here you have, so this part is kind of the compute node. So they have just shown 3 different kinds of compute nodes because there are some GPU nodes as well, and there are some high memory nodes as well. But anyway, so this is our compute node. And here is our storage. And this is what they have, they are showing the networking switch, which is being used to connect, the left and the right. So in the right, there's also some service node and so on, right? So the supercomputing ecosystem, right? So what all goes on in the ecosystem? So let me just talk about that a bit. Firstly, there are multiple jobs running, right, in the system. So for that, you need the job schedulers that will be running, that will be scheduling your job. So some of that, the job scheduler is a complex software, and some of that runs on the on these server management nodes. Some of that runs on the compute nodes and so on. And then there is storage. So some storage component runs on these server management nodes as well as on the compute nodes, because you need to route the traffic from these compute nodes to the storage, right? And so here it's not very clear, right? You have, let's say you have about 200 nodes here, right? Now you can see that, okay, there is a switch that is used to connect the compute nodes to the storage, right? But what many systems, what they do is they designate certain part of the compute nodes as the service node, which are actually part of the network topology itself. So what that helps us, those are called IO forwarding nodes, which means that they are close to the compute, and they can forward the traffic, whatever is arising from all these compute nodes, to the storage. So that so this was around 2005. This had been first developed, this kind of architecture, and this has continued in most of the major supercomputing sites. um, and okay, so that is about the storage. Now about the job allocation, right? So one thing to remember is, like I have been saying, there will be multiple jobs, several jobs running at the same time, right? Which means there will be a lot of interference. There will be jobs coming at, I mean, the submission times depends on the users when you submit your job and so on. So the usage of the system, right? It kind of depends on also on how many, so what are jobs are running currently, right? And then maybe you have a queue of jobs. So there's a scheduling policy that looks into the requests. The requests are mostly in terms of compute time. How much compute time do I require on the node? Very similar to what you have studied in OS, right? But that was on the from the perspective of one single node. So this is from the perspective of all these hundred of thousands of nodes, right? So maybe someone just require 2 nodes, and some application requires 200 nodes, right? But you have to schedule. You have to schedule in a way that you do not starve any job, right? And you are fair to the users. You also take care of high utility or high utilization of your supercomputer, because after all, it's $1 million system, right? So you don't want to let the system idle, right? So this job allocation itself is a big research area in this context. Okay. Okay, so any questions on this? All right, so we'll move forward to the next slide. This is just, yeah.
Param uses which processor and which GPU?
So Param uses Intel Xeon Cascade Lake processors and NVIDIA Tesla GPU. Param Sanganak, I'm talking of Sanganak. There are lots of Params. Okay. Okay, so this is just a little deep dive of what I told you about the IO ecosystem, right? So remember, we do not have, so this left side figure here is the compute node rack. And remember, we do not have any storage attached. The storage is here, okay? And here what you have is a switch, the network, the InfiniBand network. InfiniBand is a very high performance network. And this is what is the IO node. So we have already learned a little bit about BlueGene queue, so I continued with that. So BlueGene queue, we have one rack here. They have a compute node, IO node separately, which basically forwards the traffic. So there is one so for 1024, so which is the one rack, right? One rack has 1K compute nodes. There are 16 nodes which are actually, which is the IO forwarding node, which are connected to this IO node. Okay. They are called as bridge nodes, and both of two bridge nodes connect to one IO node. Anyway, so exact details are not important. The point here being just to make the system, the overall system, scalable. That is, here we are talking of storage. We are talking of storage from maybe 10, 20, 30 different applications. They are reading, writing at the same time, sharing the network and accessing the data from this, accessing the data from this file system. So to make that happen, seamlessly or scalable, right? There goes some amount of research as well, right? Okay, so with that, maybe I'll move on to the kind of the final slide. So here what I am showing is what I just told about the job allocation. So the top portion here, this is showing the usage of a supercomputer called Theta, which is installed in Argonne National Lab and which uses the Intel's Knights Landing processors as the computation unit. And these colors, one color represent one job. Here you can see there's a bar which kind of shows each of these jobs, how many nodes it's occupying and so on. So this is, remember, it's just a schematic view. The real system is not so organized in some sense, right? We have a lot of networking and so on. But anyway, so this is a schematic view where you can see there's some rows and columns and so on. This is a Cray system, so they have this notion of cabinets and chases and so on. And this uses Dragonfly network topology. You can see there are some more details about this. So there's some job ID, like you have a process ID when you talk about single node system. So you have a job ID, there is some project associated, how many nodes it's running on, when did it start, what was the runtime it asked, right? And sorry, what was the runtime it asked is the vault time, and how much it has run is the runtime, and what queue is it using. Oftentimes there are different queues being used, like you have heard about priority queuing. And so similarly, there may be different queues used for a system and so on. Okay, so with that, I will leave you with just one thought, which is finally a parallel with all this complexity behind, right? What we want to think about is it's a collection of processing elements that communicate and cooperate to solve large problems fast, very nicely put together by these two authors. And with that, I will end my talk for this session. So if you have any questions, we have about, I think, 10 minutes or so. So if you have any questions, now is the time to ask.
Thank you, Professor Preeti, for the overview about distributed architectures. And there is one question. I'm not sure if you have already answered that one in the chat box. Hello, hi, Preeti, can you hear me?
Yeah, so can
Yeah.
high performance computing be used for high cyber attacks? So if you are asking about the computation involved, sure. But if you're asking for a security point of view, there's generally so the Naman Purohit, can you please clarify your question? What exactly is the question? Are you asking about the computation?
Both, ma'am. Both computation as
So
well as.
computation, of course, surely, I'm not sure. So one thing about supercomputers is you need a way to parallelize, right? If your problem is parallelizable and you can run it on the supercomputer, of course, you can run. I haven't seen many of these, but it can be. If you can parallelize your problem, you can definitely use. And what is the second question actually? Are you talking about what is the security?
Both aspect means
Right.
how
So
can
how do
compute.
you make the system secure? So like any cluster or institution, there's typically a firewall. There is not there is very recently. I mean, people have started talking about security in a supercomputer, uh, but there's not much in the middleware or in the runtime systems. Like, for example, even the you can say that in some sense the job, whatever software or whatever middleware is running, there's no additional attention to security, right? Um, but yeah, so it's so of course that it's behind a firewall. More than that, did you have any other question regarding that?
No, ma'am, not yet.
Uh,
I was
ma'am,
thinking that
Go ahead.
I
if
have a
process parallelly means high, we can compute very fast. So if we have to make an attack, so we can make an attack through this powerful kind of
No, but
computing.
how will so this is what I'm trying to understand. What do you mean by make an attack? Where? To which process? So remember, you are running a job. If your job has been allocated nodes number 1, 2, 3, you cannot run anything on any other node. You are assigned to nodes number 1, 2, 3. That's all. That is your arena.
Yeah.
Okay, so that is why there's not a lot of research on, oh, if I run a malicious script and I will run something on some other node, that is not going to happen.
Yeah, so
Okay.
it does not mean that if we have lakhs of codes, so we can, if we are assigned only someone, so we
Yeah,
can.
so there's the other aspect where you are sharing a node. Of course, there you have similar problem to what you have in a node, but that is very rare in supercomputing systems. We do not share nodes because we don't want to interfere with the other jobs for that purpose. Of course, it's allowed in some systems not allowed, and so on. Okay.
If we are sharing, then it can happen. Means
I wouldn't say that it can happen. Um, um Well, I have not really heard about security issues, but of course, because you have, I mean, you are running on in the same node, same memory. Yes, there is some chance that definitely there's some chance there is, yeah. If
okay.
yeah,
Thank you, ma'am. Thank.
somebody else had a question before I answered the chat question.
yes, ma'am. I
Yes.
have a question regarding Param Shakti and Param Sangran computer.
Yeah.
They have different numbers of nodes. That means 442 for Shakti and
Right.
312 for Sangran. Then how they can have same peak performance?
Oh,
They
okay.
have
Yeah, that so I mentioned one small point, which was Shakti was installed, I think, a little earlier than Sanganak. So you have, so one thing is we have the latest CPU as well as the latest GPU, Sanganak, whereas Shakti was installed, I think, a little earlier. So that could be one reason. Okay, there is a question on the chat. In such system, how the network links and routing implemented? Huh. It's a combination of both. It's actually in BlueGeneQ, the on chip, the FIFOs that I showed, it's actually implemented in the hardware. That's for performance. So they have another layer. Okay, maybe I shouldn't go to too much details. It'll just confuse. But yeah, so some of it is implemented in the hardware. Any other question? Okay, if not, maybe I'll pause here for half an hour and then we'll resume back.
Yes, that is fine. Thank you, Professor Preeti.
Okay, thanks.
Yeah, so I will be stopping the recording now.
Yes, yes.
Yeah.